3.14 The Pythagorean Theorem. Today we're going to be able to use the Pythagorean Theorem and the converse of the Pythagorean Theorem. Take a look at this warm-up, pause the video, and answer the question. What information is required to use the Pythagorean Theorem? Check all that apply. A right angle, all three angles, two side lengths, hypotenuse. The two correct answers is it needs to be a right triangle, it must have a right angle, and you have to have at least two side lengths. A common misconception that students have is that you have to have the hypotenuse. That's false. You do not need the hypotenuse. That could be one of the side lengths that's included, one of the two side lengths, but it's not required. So Pythagoras of Samos was a Greek mathematician and philosopher who discovered one of the most famous rules in mathematics, the Pythagorean Theorem. Here's a depiction of Pythagoras in the BC era. So this has been around a very long time. They used it to calculate areas of farmlands and agriculture is why it came about. But now we use it for all sorts of mathematical tools around right triangles. In the world, we use right triangles a lot because we use rectangles and squares a lot. And the building blocks for a rectangle and a square is a right triangle. So here's what the Pythagorean theorem states in words. In any right triangle, the sum or the addition of the sum of the squares of the lengths of the legs is equal to the square of the length of the hypotenuse. In algebra, it states a squared plus b squared equals c squared. The sides of a right triangle, here's a depiction of it. These two sides are called legs. We could call this one leg A and this leg B. These could be switched. This could be leg B and this could be leg A. The one that has to be a particular letter is C. The hypotenuse is the most important part of the formula. It has to be the one that's on the other side of the equal sign. So we've got two legs and the hypotenuse. How do you know which one's the hypotenuse? How you know is that it's the side that's opposite from your 90-degree angle. So it points to it. The 90-degree points to your opposite side, which would be your hypotenuse or C. Find the length of the hypotenuse of the triangle. 15 and 8 could be A or B. So I'm going to call it A for 8 plus 15 squared for B equals our missing side length of C. 8 squared is 64. 15 squared is 225. 64 and 225 is 289. And then we want to undo a square. We want to undo this with a square root. Most calculators, when you're trying to take the square root of something, you usually have to use this second button. So take a look at my calculator here. I've got this second button, and then right above my square button, x squared, there's a blue square root right there. So first you have to hit the second button. Let me scoot that down so you can see. You hit the second button and then the x squared button, and it will pop in your square root for you. So the square root of 289 is 17. Oops, I wrote 15. Go ahead and pause the video and try letter B on your own. Now we're going to switch gears and we want to find a missing leg or a missing length from the triangle. So notice on these ones, across from the 90-degree angle is given a hypotenuse. So this 2.9 has to be my C value, and then A and B could be either one of these. They've given us a letter A, so we'll just call 2.1 B. So we've got A squared plus 2.1 squared equals 2.9 squared. And now we're going to solve that by doing 2.1 squared. So a squared, 2.1 squared is 4.41. 2.9 squared is 8.41. And then on these problems, I'm trying to solve for a, that missing side length. So I need to take the 4.41 off with subtraction on both sides. So then those cancel, and we're left with a squared equals 8.41 minus 4.41, which is just 4. And then we take the square root, and a equals 2. Go ahead and pause the video and try the second one on your own. Awesome. So above all these problems up here, we've been getting nice round numbers for our answers. And anytime you get these nice round numbers, they are what's called a Pythagorean triple. A Pythagorean triple is a set of 3 numbers that will always satisfy a squared plus b squared equals c squared. Here's some common Pythagorean triples. 3, 4, 5, 5, 12, 13, 8, 15, 17. That's actually one we saw right here. 8, 15, 17. And then we also saw the 5, 12, 13 here, 5, 12, 13. You can also do the multiples of these Pythagorean triples and they still create Pythagorean triples. I have these two memorized, 3, 4, 5 and 5, 12, 13. I would say that those ones come up the most. Let's just prove it to ourselves that these work one more time. So 3 squared plus 4 squared equals 5 squared. Is that true? 3 squared is 9, 4 squared is 16, 5 squared is 25, and 9 plus 16 is 25. So this 3, 4, 5 satisfies the Pythagorean theorem. So 3, 4, 5, 5, 12, 13, 8, 15, 17, and 7, 24, 25. Those are the common ones. There are more out there in the world. These are just the ones that are the most common. So what if it doesn't come out to a nice round number? What if it's not a Pythagorean triple? So 7 and a hypotenuse of 14 is not a Pythagorean triple. One of the Pythagorean triples was 7, 24, 25, which is not this case. So we're still going to set it up the same way we did before. So opposite of the 90 degree is the 14, which means that this value here has to be my C value. And so then 7 and x could be my a or my b. So I'm going to say, I'll make 7a squared. So 7 squared plus x squared equals 14 squared. 7 squared is 49. 14 squared is 196. And then subtract 49 from both sides. And then that's the square root, or it's going to be the square root of 147. So we'll take the square root of both sides. And when we go to our calculator to take the square root of 147, the square root of 147 is 12.124355565 and more after that. So when we write our answer for this one, we should not put an exact equal sign. We should put the approximate symbol because we're going to approximate this answer. Let's take 3 decimal places. 12.124. This is an approximate. An approximate answer means not exactly all the decimals in the world that came with this answer, 12.124. So I want to talk about how do you politely write answers instead of needing to use a calculator? Or like what happens if you don't have a calculator to take the square root of 147? So this process is what's called simplifying a radical, and we are going to practice simplifying radicals. What it does is it takes an answer like the square root of 18, which is also not a nice number. So the square root of 18 is 4.24, blah, 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 blah. What we're going to do is we're going to simplify this square root of 18 into a nicer number that I don't need a calculator in order to simplify it. So what you're doing is you're going to break down 18 into what's called its prime factor tree. Some prime numbers, starting with 1 is a prime number, 2 is a prime number, and 3 is a prime number, but 4 is not. 4 is composite. It's comprised of 2 and 2, and we skip to 5 is a prime number. 6 is not a prime number. It's composite. It's comprised of 2 and 3, but 7 is a prime number. And then it continues on. There are prime numbers infinitely in the world. Let's just list like 2 more. So 8 is not, 9 is not, 10 is not, but 11 is a prime number. 12 is not, but 13 is. So this is a ... That list continues on forever. There are lots of prime numbers out there in the world. One that comes up, I'm going to skip ahead. One that comes up a lot is 21. That's a pretty common prime number that you might see out there. So I'd like to break 18 up into its prime factor tree. So I'm going to make an actual little tree. I'm going to split 18. The best way to do it if it's even is just to start with 2 and just say 2 times what is 18? 2 times 9 is 18. 2 is prime, so I'm going to circle my prime number because that's the end of one of my trees. 9 is not prime, it's composite. It's broken up into a 3 and a 3, which are each prime. So now my tree is complete because I've got all the ends of my tree broken down. So what we've done is we've broken 18 into its prime factors. 2 times 3 is 6. 6 times 3 is 18. Or I could go the other way. 3 times 3 is 9. 9 times 2 is 18. So I can rewrite 18 as 2 times 3 times 3. It's the same thing. 2 times 3 times 3 is the same thing as the square root of 18. Well, 3 times 3, those go back. 3 times 3 is 9. So I could even rewrite this one more time as 2 times 9. Now, 2 is a prime number, but 9 is a perfect square. 3 times 3 is 9. So what I can do is I can break this up again. I can say the square root of 2 times the square root of 9. The square root of 2, that one's not going to break down, but look at this. The square root of 9 is 3. So 3 with the square root of 2. 3 square root 2 is the simplified radical of the square root of 18. You can check it in your calculator to see if they're the same number. So I already have the square root of 18. Oops, it was 2 root 3. And 2 root 3, whoopsies, 3 root 2, I typed it in right. Okay, let's try that one more time. Square root of 18 and 3 root 2, those are the same number. They're the same number. The square root of 18 and 3 root 2 is how you say that. Let me write that down. So you say this as 3 root 2 is how you say that number. 3 root 2 is the simplified radical of the square root of 18. Let's try another one a little faster. I might write it slightly different. What you're looking for is pairs of 2, because if you have 2 numbers underneath this radical, 3 times 3 is 9, or say you had 2 times 2. 2 times 2 is 4. The square root of 4 is 2. Let's say you had 5 times 5. 5 times 5 is 25, and the square root of 25 is 5. So you're always looking for pairs of 2 underneath this radical. So let's try this one. So the square root of 12 breaks down into a 2 and a 6. And the 2 is prime, but 6 is not. 2 and 3. So I can see I have a pair of 2's and a 3. So those 2's, 2 times 2 is 4. So I know that's the one that's going to be the square root of 4, which is 2. Every time you take the square root of these, it becomes the number itself. So for example, like on this one, the 3 times 3, what happened is that 3 came out in front of the radical as just one single 3. Because one more time, listen carefully. 3 times 3 is 9, and the square root of 9 is 3, actual 3. So here we go again, 2 times 2 times 3. I'm going to use the little dots. I've got a pair of 2's, which creates a perfect square. 2 times 2 is 4, so I'll write it again, the square root of 4, square root of 3. And the square root of 4 is 2 with a root 3. Square root of 72, 2 and 36. Why don't you finish this one? See if you can pause the video and finish it. 2 and 36. On this one, we've got several groups of 2's and 3's. So I've got 2 times 2 times 2 times 3 times 3. So on this one, I've got a pair of 2's and a pair of 3's. 2 times 2 is 4. 3 times 3 is 9, which gets me back to 4 times 9, which all the way back up into my tree is 36. This is a perfect square. The square root of 36 is 6. Also, I can see it right here. When I pull these out front, it becomes a 2 times 3, 2 times 3, with a leftover 2 there. So my final answer would be 2 times 3, which is 6 root 2. And I could see it back up in my tree here, the square root of 36 times the square root of 2. The square root of 36 is 6 with a leftover square root of 2. Square root of 40, 2 and 20, 2 and 10, 2 and 5, 2 times 2 times 2 times 5. I got a pair of 2's. 2 times 2 is 4. The square root of 4 is 2. And then the 2 and the 5 are not a match, so we just multiply those back together to make 10. 2 root 10. 2 and 54. 2 and 27. 27 breaks up into a 3 and a 9. 3 and a 3. So then I've got 2 2's and 3 3's. I got a pair of 2's and a pair of 3's. We've seen this before. 2 times 2 is 4. 3 times 3 is 9. 4 times 9 is 36. And the square root of 36 is 6 with a leftover 3. Or 2 times 3 is 6 with a leftover 3. 5 and 27, 3 and 9, 3 and 3. 5 times 3 times 3 times 3. I've only got one pair of 3's right there. 3 times 3 is 9, and the square root of 9 is just a 3. Whoops. And then the 5 and the 3 go back together to make a 15. 3 root 15. So I'd like you to pause the video and I'd like you to try to answer this question. I'd like you to give me both the simplified radical answer and the approximate answer for this problem. So you should have gotten to the square root of 80. The square root of 80 in a calculator as an approximate is 8.944. But then if I do it as a simplified radical, you should have gotten 4 2's and a 5. 2 times 2 is 4. 2 times 2 is 4. 4 times 4 is 16, and the square root of 16 is 4, or 2 times 2 is 4, with a leftover 5. So 4 root 5 is an exact answer. All of these are all considered exact answers, no approximating necessary. So I don't use the approximate symbol to represent those. All right, the last part is the converse of the Pythagorean theorem. If the square of the length of the long side of a triangle is equal to the sum of the squares of the lengths of the other two sides, then it's right. So what they're saying is that if it satisfies a squared plus b squared equals c squared as a Pythagorean triple, then it is a right triangle if it satisfies this equation. But if it does not satisfy this equation, if it's not equal to, then it is not a right triangle. So it says tell whether each triangle is a right triangle. So on this one, here's my 2 shorter legs and my longer one. And I want to know, is 65 squared plus 72 squared, let's try this again. 65 squared plus 72 squared, is that question mark equal to 97 squared? Well, 65 squared is 4225. 72 squared is 5184. And 97 squared is 9409. And then if we add these together, 4225, 5184 is 9409 is equal to 9409. So this is a right triangle. So I can put the right angle symbol on my diagram there. Check, this one works. You check the second one. Is this triangle a right triangle? .4 is not equal to 529, so this is not a right triangle. So I cannot put the right angle symbol in there. Thank you.